A particle is projected from a point on the horizontal ground with speed u meters per second at an angle 30 degrees to the horizontal. The particle is at a height of 7.35 meters above the ground at times t1 and t2 seconds. So we are given that the difference in those times is 1.5. So clearly at time t2 the particle must be here, and at time t1 it's here, because t2 must be greater than t1 for the difference to be positive. So we're given the y displacement of the particle. It's 7.35, so that's sy, or we could just write y here. And as usual, we treat our projectile motion as a vector sum of linear motion in the y direction and linear motion in the x direction. So here's the formula for linear motion in the y direction with constant acceleration. The constant acceleration in the y direction is the acceleration due to gravity, which we know is vertically down and has magnitude 9.81. Okay, so again, upwards directions are taken as positive. Okay, so now we know what sy is, we know what uy is. Uy is the y component of the initial velocity, so that's just u sine 30. Okay, the magnitude of the velocity is u. Ay is 9.8, so we get minus 4.9 t squared. So normally what we would do is solve this quadratic equation for t. We would get two solutions corresponding to the two times when the particle is at a height of 7.35, unless of course the height happens to be the maximum height. In that case there's only one solution, there's only one time for that. Okay, so let's just follow that procedure anyway, even if we don't really know what we're doing. Okay, the next bit is routine, even if there's quite a bit of algebra. So here we have a quadratic in t. I've just written it in standard form. I've made the t squared term positive, but of course you don't have to. So we use our formula minus b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. Sine of 30 is a half. Okay, so depending on whether we take the plus sign or the minus sign, we have the 2 times for which the height is 7.35. So does the plus sign give us t2 or t1? Well, half u is positive, so if we add something onto it we make it greater, of course. You know, if we subtract we get a smaller result, so we're either adding or subtracting a quantity from something that's positive. Okay, because u is the speed, that's the magnitude of a vector, which is always positive. So it's clear that t2 involves the plus sign. So let's get t2 minus t1, because we know that that's equal to 1.5. So we subtract t1. So that's this quantity with the minus sign. So if we do the subtraction, we get minus a half u here, and we're subtracting minus the square root, so that we get plus the square root of a quarter u squared minus 144.06. So these terms cancel out. Okay, half u over 9.8 minus a half u over 9.8, and we add the two square root terms. Of course we still have the 9.8 denominator. So we set this equal to 1.5, that's what we're given. Multiply both sides by 9.8, square both sides, and solve for u. In this problem we have an inclined plane at angle beta to the horizontal. A particle is fired at angle alpha to the inclined plane, and it strikes the inclined plane in such a way that the final velocity is horizontal. Now, since the final velocity is horizontal, this angle in here is beta. So as usual, we take the positive x-axis to be up the incline and the positive y-axis to be perpendicular to the incline. Let's look at the components of the final velocity vector. Well, we can see that the y component is negative. That's the component that's perpendicular to the incline. Okay, the positive y-axis is pointing away to this side of the incline, so this component is negative. Here's the x component. So Vy, the y component of the final velocity vector, is going to be v sine beta, because Vy is opposite beta in this right angle triangle. And the x component is going to be v cos beta. Of course, this is negative here. V is the magnitude of the vector. It's the final speed. That's positive, of course. So we could write the final velocity vector like this. Here's the x or I component. It's positive. And here's the y component. Now, as soon as the particle is launched, the only force acting on it is gravity, which is vertically down. So the resultant force is vertically down, so the acceleration is vertically down, and we know that that's g for all objects near the surface of the Earth. Now we are going to be interested in resolving this vector, this acceleration, in the x and y directions. So the y component is perpendicular to the incline, and the x component is parallel. Now I'm going to exaggerate vector g so it's easier to see. Now this is an exaggeration. It could be completely out of scale compared to the other vectors, but it doesn't matter. Well, of course, the units of vector g are different from the units of the velocity vector. So actually I'll show vector g in black and its components in the other color. Okay, now to get its components in the y and x direction, we need this angle here. Now this angle is the same as the angle of the incline. This angle in here is beta. Now I explained this in other videos, but I'll just go through it again. We have a pair of lines that are perpendicular to this pair of lines. Okay, this line here contains the y component of the vector, so by definition that's perpendicular to the x-axis, and g itself is perpendicular to the horizontal. Okay, so the angles between the two pairs of lines must be the same. So anyway, right, so the y component is negative. Okay, this is a positive y-axis, so the y component is going to be, well, I'll just write down the magnitude of it. It's g cos beta. It's the hypotenuse times the cos. It's adjacent to angle beta, and the x component is opposite angle beta, so its magnitude is g sine beta. So I'm just writing in the magnitudes here. So here's our g vector written in terms of the xy coordinates. Okay, both components are negative in terms of this particular set of xy coordinates. So we want to prove this relationship between angles alpha and beta. So we exploit the fact that well, okay, we're interested in what happens here at this point. At the y coordinate of this point is 0, or we could say the sy coordinate is 0. So sy, as we know, is uy times t plus a half ay times t squared. So this is a formula for linear motion with constant acceleration, so we're just dealing with the y component of the motion of the projectile. Okay, so the y component has constant acceleration ay. That's actually given by this vector here. So basically we're looking at the forces on the, we're just resolving, well, the force on the particle is vertically down, but we resolve that force in a direction parallel to the y-axis, because we want to know what happens here. This is where sy is 0, so we're looking at this formula for the y coordinate. From this formula we can solve to find t, the time of flight. And if we know the time of flight, we can use our formulas for v equals u plus at, we can use the fact that, you know, the final velocity is horizontal and plug the time that we found solved from this equation into this equation here. Well, we need to consider the x and y components of this equation. Okay, so that's the strategy. So we're looking, basically we're just resolving the force on the particle in the y direction and in the x direction. So that just means resolving the acceleration of the particle in the y direction and the x direction. So force is really just synonymous with acceleration. We just have this constant factor m by Newton's second law. So let's get our expression for the time of flight. We need uy, the y component of the initial velocity. Well, that's u sine alpha. We need ay. So the magnitude of ay is g cos beta. So we just minus it. So we minus a half g cos beta. Okay. Of course, we know what to do here. We just factorize t out of this. So one of the solutions is t equals naught. Okay, that's when the particle is here. We don't want that solution. By setting the other factor equal to naught, we get t equals 2u sine alpha over g cos beta. So again, all I did was look at the y component of the particle. Okay, so the y component of the particle's initial velocity, the y component of its acceleration, which is constant. So it's like we're dealing with motion on the y-axis. It's uniform linear motion. That means linear motion with uniform or constant acceleration, where the constant acceleration is ay. Okay, and it's negative. Okay, so now we have the time for the particle to get to here. Now what happens when the particle, just before the particle strikes? Well, its velocity is horizontal. So let's consider the y component of the particle's velocity as it moves. Okay, again, we've linear motion with constant acceleration if we look at the projection of the particle onto the y-axis. So we can use this formula from the section on linear motion. So the y component of the initial velocity is u sine alpha. The y component of the acceleration is negative. It's minus g cos beta. We can also see it from up here. And that's multiplied by t, the time of flight. So now we're going to, the Vy we're interested in is the Vy just before the particle strikes the incline. And that Vy happens at this time. So we plug in the time of flight. And we set this equal to Vy when the particle strikes, which is minus v sine beta. So after the cancelling, we've u sine alpha minus 2u sine alpha is minus u sine alpha, and I've just written, made u the subject of this, so this relation will come in handy soon. So we looked at the y component of the final velocity. Now let's look at the x component. So the final velocity in the x direction is the initial velocity in the x direction plus the acceleration in the x direction, which is constant, times the time of flight. Well, we're going to be plugging this thing in. So the x component is u cos alpha. Now the acceleration in the x direction is negative. You can see it's pointing down the incline in the negative x direction. And we multiply this by the time of flight. And that gives us the x component of the final velocity. You can see it's v cos beta. It's positive. Now I can do a small bit of simplifying here. G's cancelled. Sine beta over cos beta is tan beta. I'll just take out the u. we're going to get minus 2 tan beta sine alpha. So next we plug this thing in for u, and v will appear as a factor on the left hand side and it'll cancel with the v factor on the right hand side, so we'll just end up with an equation connecting alpha and beta, and that's what we want. Now our final equation just involves tan functions. So the tan of an angle is sine of the angle divided by cos of the angle. You see, we've this lone cos term out here, so if I can put this over sine, well, sine over cos is tan, but cos over sine is just 1 over tan. Okay, so I just want to bring the tan function into this equation. So to do that, just divide everything by sine beta, and we're going to use the fact that tan beta is sine beta over cos beta, or we can invert this to get 1 over tan beta, etc. So if I divide this by sine beta, I get 1 over sine alpha, and I'll take the sine alpha in here and we get cos alpha over sine alpha. Now that's just tan alpha turned upside down, or 1 over tan alpha. And okay, so this sine beta is gone, remember, because I've divided the left hand side by sine beta, and the v is gone. So we've cos alpha over sine alpha, and here the sine alphas will cancel. Okay, so I've just taken in 1 over sine alpha, and we've cos beta divided by sine beta, so that's just 1 over tan beta. Okay, so we isolate 1 over tan alpha, shift this term over, get a common denominator of tan beta, so write these two fractions as a single fraction. Finally, we just take the reciprocal of both sides to get the result. Now part 2 is actually very easy. We just note that this fraction here is obviously less than tan beta. There's nothing really physical going on here. It's just tan beta is divided by something that's bigger than 1. Okay, tan squared beta is a positive number, and we plus twice that positive number is obviously a positive number, so it's clear that the denominator is bigger than 1. So if you divide something by something that's bigger than 1, obviously what you will end up with is something less than what's on top. So if we divide tan beta by something that's greater than 1, we get something that's less than tan beta. And if this is less than tan beta, then obviously tan alpha, which is equal to this, is less than tan beta. Here we have an incline at angle beta to the horizontal. Beta has a value. It's given by tan of beta equals a half. A particle is launched at angle theta to the incline. The speed is fixed. The speed is u. So what varies is theta. So we're interested in the value of theta that maximizes the range up the incline, that maximizes this distance. So you can see the positive x-axis is up the incline, so we want to maximize s sub x, that's the horizontal or the x displacement of the particle. So again, we can imagine different scenarios. You know, the particle might be launched at this angle, but these vectors have the same magnitude, or it could be launched at this angle here. So we want the launch angle that maximizes the range. Okay, so let's get the range in terms of u and theta. So we saw how to do this in a previous video. Well, we did it for the case of no incline, but same reasoning. So first of all, we want to find the time of flight. So when the particle strikes the incline, we know that the vertical displacement, well, not the vertical displacement, the y displacement here, because y is not vertical, it's perpendicular to the plane of the incline, is 0. Okay, so we set sy equal to 0, and we can get the time of flight in terms of u and theta. So again, as I've mentioned several times before, we use our kinematic formula for linear motion with constant or uniform acceleration. But we're only looking at the y component of the acceleration of the particle. Okay, and that y component is constant. So let's just go back over this again. Say that when the particle is here, the acceleration is always constant. It's vertically down. It's got magnitude g. We get its two components. It's x and y components. I'll use a different color for the components. We know that the angle in here is the same as the angle between the incline and the horizontal. I explained that a few times. This vector here has magnitude g cos beta, whereas this one here has magnitude g sine beta. Now in terms of the x and y coordinate system that we have here, the two components are actually negative. Okay, so we can write the acceleration like this. I could call it g, but actually I'll call it a. So this is the ax component and this is the ay component. We also need uy, and later on we need ux. But uy is just u sine theta. I'll also factorize out to t. So you have a half times ay, that's minus a half g cos beta. And that's multiplied by t squared, but I'm factorizing out a t. Now we've seen this before. The product is 0 for this quadratic equation, so one solution is t equals 0. So t equals 0, sy is 0. Well, we don't want that, of course. Put the other factor equal to 0, and you get 2u sine theta over g cos beta. So you could just memorize this actually for the time of flight. Comes up quite a lot. Okay, so we want the range. Now we can get the range using this formula. So we plug in the time of flight into the displacement formula in the x direction. So again, we're dealing with just linear motion, just the x projection of the particle. Okay, if you imagine the particle projected on perpendicular to the x-axis, and imagine how that projection moves. Okay, so that projection depends on the initial velocity in the x direction, that's ux, and it depends on the acceleration in the x direction. So we need the x component of the acceleration. Okay, that's minus g sine beta, which is constant. So we're dealing with just linear motion really. The projection moves at moves linearly, you know, on a line with constant or uniform acceleration ax. So ux is u cos theta, and we plug this in for the time of flight. So we've minus a half ax, that's minus a half g sine beta. And then we have the time of flight squared. Now, the only variable in this expression is theta. So the range s sub x is a function of theta. Actually, I could just call the range r, because we're getting the maximum value of s sub x. Well, s sub x is the range, so r is a function of theta. So, you know, I've taken the constants out. U is a constant. Obviously, g and beta are constant. Beta is a given. We can plug in for that actually, because tan beta is a half, so we can get cos beta as a number. And over here, then I just want to take out the part that varies. That's the sine squared theta. So let's square this thing out. Okay, we cancel one of the g's here. Just have to be careful here. Okay, I'll fill in for the cos beta. So tan beta is opposite over adjacent. So the hypotenuse is root 5. So cos beta is 2 over root 5. And over here we have to square 2 over root 5. So that's 4 over 5. Okay, the 2's cancel. If I multiply above and below by root 5, this will go out. So we'll have root 5u squared over g. Okay, if we multiply above and below by 5 here, we'll have 5u squared sine b over 2g. I've nearly forgot about the sine beta. That's 1 over root 5. Now 5 can be written as root 5 multiplied by root 5. So we cancel one of the root 5, so we get root 5u squared on top. To find the value of theta that either maximizes or minimizes this expression, we have to solve this equation. We differentiate r with respect to theta and set the derivative equal to 0. Okay, we know that from calculus. If we imagine a graph of r against theta, well, at a local maximum, the slope of the curve, which is the slope of the tangent to the curve, is 0. Okay, the slope of the curve is the derivative. So by solving this equation, we can find this value of theta that gives a local maximum, or indeed it could be a local minimum, but we will see that it can't be a local minimum. Now, notice that we have a product of functions here, so it looks like we have to use the product rule. However, we can get around it by using an identity for cos theta sine theta. So you can look up this identity. So we can write this thing here as sine 2 theta divided by 2. Sine 2 theta is 2 sine theta cos theta. Okay, I'll just tidy this up a bit. Okay, now this is just a constant factor. We just leave it to one side, of course, because u is given to us, u is fixed, speed is fixed. If we differentiate the sine function, we get the cos function. But we have to multiply by the derivative of the angle. The derivative of 2 theta is 2. We have this constant here that we set to one side and differentiate sine squared theta. Now, we use the chain rule on this actually. We deal with the power first. We take the power in front to get 2 sine theta. Okay, it's like we just differentiated the power. Of course, we don't normally show a 1 here. Okay, so it's like we're differentiating with respect to theta sine theta squared. Okay, we're just using the chain rule. So we differentiate around the brackets, if you like. You could say that, and multiply by the derivative of what's inside. So the derivative of sine is cos. So we have to set this equal to 0 and solve for theta. Now we can divide all of this equation by root 5u squared over 2g. Indeed, we can divide by this 2 as well. Okay, so we have to solve this equation. Now, usually when we try to solve a trigonometric equation, we try to get all the angles to be the same. All the angles or arguments to be the same. So we'll use an identity to do that. And when we've that done, we normally try to get the functions to be the same. Okay, so I'll work with just making the angles the same. So, this, we've seen this already, this product of sine and cos. See, 2 sine theta cos theta is sine 2 times theta. So we can write the product of sine and cos as a half sine 2 theta. So now the angles are the same. The angles are the same, but the functions are different. However, we can write this equation just involving a single trigonometric function. We use the fact that tan theta, or 2 theta, is sine over cos. So what we can do here is divide all of this equation by, well, actually I'll rearrange it first. And the next thing we do is just divide both sides by cos 2 theta. Okay, so tan 2 theta is sine 2 theta over cos 2 theta. So if we solve, we get that theta is 31.7 degrees. So if we were to draw a graph of r against theta at 31.7 degrees, we would have either a local maximum, which is actually what we do have, or we could also have a local minimum. Okay, at both points the slope of the tangent or the derivative is 0. So how do I know that it's a local maximum rather than a local minimum? Well, we can see from the context of the problem. The particle is launched at some angle theta. You know, if it was a minimum, well, theta would look very different, of course. You know, we could imagine launching it maybe just straight up. Okay, the particle will go straight up and fall back down again. So the range is 0. The initial position, x position was 0, and the final x position is 0. Okay, so this would be the situation, and we can easily find that angle, because in this situation these two angles add to 90 degrees. As a matter of fact, at 63.4 degrees the range is 0. Okay, beta is actually 26.6 degrees, so we subtract that from 90. This point is not actually a local minimum because the range can be negative, but I'm kind of getting beyond what we need to know for this problem. But anyway, you can take it that we have a local maximum at 31.7 degrees, and if we want to find the range, of course we just go back to the expression for the range. So here it is. So we could just plug the value that we got in for theta and we'll have the maximum range in terms of u, of course.